So thanks everyone. Thank you for the invitation and for being, for having me here. So today I want to tell you about keeping matter in the loop and 3D quantum gravity. This is based on two papers that we put out earlier this year. And there will be a lot of moving pieces. I will say a bunch of stuff. I hope I don't confuse you and you stay in the loop with me. But if you forget things, which is fine, what I do want you to remember is these three collaborators that I have that are fantastic, Joanna, Jackson, and Claire. And hopefully towards at the very end, I will tell you also about some things that I'm thinking and working with Jackson here. But okay, so let's get started. I don't have tons of time. So the basic question that we were studying is basically to understand how does quantum gravity alter the physics of matter fields. Okay, so very pictorially, you can think of basically you have some scalar field propagating on a fixed curved background. And what we want to understand is basically what are the effects of loops as that field propagates around. Okay, now the punchline of this talk is basically that I will tell you how to carry out this computation using Chern-Simons theory. Okay, this is a compelling way how to proceed. It will be something where I would actually be capable of evaluating the series with quite a lot of precision. Now, during most of the talk, I will have to motivate the construction and the proposal. We'll look at basically what is this computation on a field curve background, but I do want to emphasize that this is not just another way how to compute a one loop determinant of a field and a curved background. This will actually allow me to compute the effects of the metric fluctuations order by order in G Newton. So, okay, so just to put a little bit more equations. So if you have a metric formulation of this problem, so what I just described, what I wanted to compute, you will basically have said, okay, so let's consider first, like what we will be considering is just a real scalar field. It will not have any interactions with itself. So if you look at its path integral on a fixed background, it's basically just the determinant of the appropriate Laplacian, including metric fluctuations is basically doing the path integral over G. And what I'm going to present to you today is basically these computations, but casted in this Chern-Simons language. And the object that will do the job for us is something that we call the Wilson spool, which you will be clear why I'm calling it a spool, which is also loops backwards. And I will tell you then basically then how to compute basically the metric fluctuations, how to do it in functions of these connections. Now, for today, I'm going to only be doing this gravitational path integral on a fixed topology, but if I have time at the end, or you can just ask me after, we can also talk about what happens when you change the topology. Okay, so I also made a compromise. I apologize. I think in the abstract, I also mentioned ADS3. The construction and the proposal also works for ADS3, but given the machine here that is controlling me, I'm going to focus the presentation today on DS3. So we'll talk about de Sitter quantum gravity. And you might ask why? Well, because I can. And the sense in which I can is because there's quite a lot of technology in SU2 Chern-Simons theory, and I'm going to make use of that, okay? And we're going to see how that's a powerful way how to approach the problem. I'll be able to make predictions on these corrections at order 1 over G Newton without having any use of holography or anything like that. And also there's some interesting aspects of this SU2 Chern-Simons theory that I'll explain you that involves in introducing non-standard representations of the algebra. Okay, so with that said, the way that this talk is going to be structured is that I'll tell you a little bit, to set up the stage and go through some of the notation. We'll talk very briefly about Chern-Simons theory and its relationship to 3D gravity. Then I'll introduce for you the Wilson spool. We'll test it, so we'll see how it computes one loop determinants, and then we'll talk about these quantum corrections. Very good. So Chern-Simons theory and 3D gravity. So this is a really old story, and basically it goes as follows. So at the classical level, at the level of the equations of motions, it has been established that basically the Einstein equations and its action written in metric formulation can also be cast in terms of a Chern-Simons formulation, where here I've written basically the basic equation of Moulton, the flatness condition, and the Chern-Simons theory, and its action. And so basically, we have this luxury of casting pure 3D gravity in either of these two formulations, at least at the classical level. Okay, this is the relationship between the two of them. Now, I'm going to be focused on DS3, and in particular Euclidean DS3. And there's some things that go into then the relationship between the two theories. So the relevant gauge group, when I have a positive cosmological constant, is basically 2 copies of SU2. Okay. And so then if I write down the action, let's say with an arbitrary level, so I have 2 copies of the SU2 theory with level K left and K right. You do your homework here, and the way that it's related to a gravitational action is that you will get the Einstein-Hilbert action plus a gravitational Chern-Simons term, and the relationship between the couplings is this one. So the level, the imaginary part of it, is actually what gives you the Einstein-Hilbert component. The real parts of the levels in the Chern-Simons theory is what gives you what I would call the gravitational Chern-Simons term here. Okay, so this is the relationship between the couplings. As we quantize the theory, these levels get shifted by a 2. Okay, so then later in the talk, as we talk about the quantum properties of these computations, you won't see K, you will see this number R. Okay, but still the imaginary part of R is going to be what you recognize as L over G Newton. Okay, and then the basic dictionary, how you relate the connections to properties of the background is via this formula. So it's basically the sum and the differences between the Einbein and the spin connection. Very good. Now, we're going to be looking, the basic background that we're going to be doing these computations on is S3. And so I wanted to just set up a little bit the rules on how do I think about the round sphere in this language of connections. So using my dictionary here, so basically this is the metric on S3 that we all know and love. If you write it in terms of connections, this is what happens. From the Lorentzian point of view, I'm basically looking here at the static patch of de Sitter 3. And what is very important, this is going to be something that I'm going to reiterate. The second thing that you will have to memorize about this talk is that these connections, they're flat connections. Of course, they solve the equations of motions, but their holonomies are non-trivial in a very specific way, okay? So the holonomy of this connection around, basically here, I'm reporting on what is the holonomy around one of the poles of the sphere, pi over 2. It's basically plus or minus 1, okay? So although the space-time is smooth, this is a regular space-time, the connections here are not trivial connections, okay? And this will be key in what goes on. Exactly. So you think, like in some sense, but this is needed. If this values would have been 0, you would not have been able to reconstruct a smooth metric out of it. So it could not have been like 0.
Just contractible if the flux is 0.
You have to like
string.
Yes.
Okay.
And in some sense, you have to think that so this is also important when you evaluate the action. So when I told you that the actions are related, in the metric formulation, the Einstein-Hilbert action is the volume of the sphere, right? And so I cannot use A equal to 0 because then I compute trace of A dA plus A cubed, then I get the volume is not 0 of S3. And the reason why you don't get 0 is because you can view it as the responsible thing is basically this little monopole that is sitting there. So what happens, and the other way that you can think of this is that when you take dA of one of these connections, there's a singularity as a distribution. So d of d phi is not quite 0. And that's basically, this is another way how to write it. And so then when you compute the Chern-Simons action, you do get the right answer that it gives you the volume of S3. No.
Okay, but the equation of motion says it's flat, so that's fine.
Locally. Okay. Oh, this is an integer, so it depends also like So it's not like I'm getting a real number here, but it's important that that integer is not 0. Okay, so this is crucial. Otherwise, everything that I'm saying will start falling apart, and you're going to be doing Chern-Simons theory, which is perfectly fine. You're not going to be doing quantum gravity. So yeah, okay, very good. So this is what I want to say about like the basic dictionary between DS3 and Chern-Simons theory, SU2 Chern-Simons theory. Now let's talk about this object, this Wilson spool. Okay, so we want to add what I told you so far is just basically pure gravity, just metric degrees of freedom, but we want to add matter. Okay, so the first exercise that you have to do is basically just think about point particles. And when we have point particles in general relativity, you're thinking, this is the object that basically follows geodesic distances in your theory of gravity. So the first question to answer is basically what replaces this notion of geodesic distance in Chern-Simons theory. So this has an answer. It has been answered for various values of the cosmological constant at different moments of time. But basically, without too much surprise, a Wilson line is the object in Chern-Simons that tells you about geodesic distances. Okay, so this is like the operator that describes point particles. And it's quite beautiful. It doesn't depend. So the Wilson line doesn't really care about like where it's going, but it's quite remarkable that as a function of the endpoints, it does give you in the large mass limit of the point particle the mass. Now, to be a little bit more precise, we're going to be looking at loops. So if you do a loop, basically this is a trace over a given representation. You can also think of it as a path integral of that point particle. And the point here, the information where you're encoding the part of this formula that tells you what is the mass of the particle is basically the representation that you're putting in there. Okay, that will tell you what m is. And so in that sense, then you can say, okay, that's great. The representation carries information of the mass, in particular the Casimir of the representation carries the mass. And so then for SU2, the Casimirs are given by, you can always label them as J times J plus 1. And then it should be, in the SU2 case, it should be basically minus m squared L squared. Now, all of us know representations of SU2. They do not, usually our favorite representations that we learn in quantum mechanics do not have negative Casimirs. They have positive Casimirs. And also, they have integer. And so these are not basically, if we want to interpret these Wilson loops as massive particles in the sitter, we're not supposed to be computing Wilson loops in the standard unitary representations that one does when you're just doing SU2 Chern-Simons theory. And so this was part of the work that we had to do to understand what are the appropriate representations if you want massive degrees of freedom in the sitter. And there's an answer. So we basically constructed something that we called non-standard representations of SU2. And here, basically, these are the appropriate representations. If you just have massive degrees of freedom, there will be 2 copies of the representation because I have 2 copies of SU2. But basically, what I'm destroying relative to what we knew about the standard unitary representations of SU2 is that I'm modifying the hermiticity conditions. So usually in the unitary representations, you would have a beautiful plus sign there. Okay, so I change the definition of the inner product. And that basically allows, for instance, in this case, in what we call complementary type representations, is to have basically now the Casimir being negative with what we call like light fields in the sitter. There are infinite dimensional representations, and here I'm basically writing the character associated to this representation. This one does have an analytic continuation to SL2, and so it's basically the familiar, you can analytic continue it and see that they're SL2 representations, complementary representations of SL2. Now here there's the principal type representations where the Hermitian is a little bit more complicated. So it's basically the Hermitian here is where you use the shadow operator that takes J to its shadow value. So this is the other representation that has the same value of the Casimir. And now here the J is a complex number, and this will describe like massive fields in the sitter. It also has it's also an infinite dimensional representation, and it has this character here. And some just important comments. The norms of these states are positive. So that's how we were trying to do the construction. So that's important for us. They're also not the Lorentzian representations of de Sitter. They are related. So you can, combinations of these characters will match the characters of SO3,1. But these hermeticity properties are not the same hermeticity properties that you impose in Lorentzian de Sitter. They're actually the same norms. They're compatible with what's called the R norm when you compute quasi-normal modes in de Sitter. Okay, so these are the non-standard representations. And so we're also introducing this as a new ingredient and when we think of massive particles in Chern-Simons theory. Okay, now that's a point particle. I want to introduce a field, okay? So how do you go from a single particle state to basically a multi-particle state? Okay, so the way that I like to think about it, so I'll basically tell you what the answer is. And so this is the Wilson spool. It looks not illuminating at all. But actually, this is something that if you want it, there's a careful derivation in our paper. And basically, you might think, why is this the logarithm of the determinant of a Laplacian? But what I want to say is that you can actually derive this. I'm not going to go through the detailed derivation because it's a little bit tedious. But for those of you that are familiar with the quasi-normal mode method for one-loop determinants, which was proposed by Denef, Hartnell, and Sachdev a few years back, you can start from there and then show that this formula here for one-loop determinant is the same as that. What I'm going to do instead is I'm going to try to give you a little bit of intuition of what are these ingredients here. So you can have a feeling of like why this thing is the right field, okay? So the way that you want to think about this is the following. So there's a part here in the formula. So I have two traces because there's two copies of SU2. But basically here I have a path ordered exponential of A left and A right. This is where you're putting information about the background, the geometry, okay? So this is where gravity comes in, okay? That's what this is doing. Then, of course, the traces here on some given representation will tell you what is the species of the field, okay? So what is the mass of the field? That's where the information M comes in. Now, the thing that looks kind of weird is this part here, okay? This integral over alpha of cosine over sine. That looks strange, okay? This comes about because you have to introduce, when you're going through the quasi-normal method, you have to introduce a Schwinger parameter. This is how alpha comes in. So basically, that's why I'm saying like my first commentary is that you have to think of alpha as something that was telling you how you're regulating UV divergences. This answer actually, with our prescription, is UV finite. It does not have a divergence. But the thing that is interesting here, and the thing that I want to give intuition, is that there's a non-trivial contour that is prescribed here that I'll show it to you in a moment, what the contour is. But what I want you to think about in terms of the sines and cosines is that the sine basically has poles, okay? So you will have poles, and every integer about 2 pi n will give you a pole. And so if you think of like this as basically, I'm doing a bunch of residues every time I hit a pole in alpha, you can very kind of like in quotes think that this is basically a 1 over n. Let's forget about alpha equal to 0, but this alpha here is basically giving me a 1 over n times n times. So alpha is also appearing up here in the exponent of n times the path order exponential. And so this gives you the interpretation of like, if n is equal to 1, I have a single particle state. Then what is a multiple particle state? Basically wind many times, okay? And that's what I'm trying to illustrate in this little cartoon here, okay? So instead of just going once around the loop, the field is basically going n times around the loop, okay? I'm writing this in quotes because you can also have contributions to the poles due to the characters themselves. So that's why this is not an equality. It happens in ADS that these characters don't give you poles, and this is exactly how you, and in ADS 3, when people compute one loop determinants, you can actually see that they're basically exponentiations of characters of SL2, which is what this formula is. But in the sitter, it's a little bit more complicated. Okay, very good. So that's our spool. Now, next test, let's compute it. Okay, so I'll tell you what the contour is. We'll fix a background. So we'll fix S3, and let's just do this computation to see what this object is on a fixed background. So the characters that I had, so I'm picking this non-standard representations of SU2. When I pick here my backgrounds, I'm going to pick here my holonomies to be plus and minus 1. And the contour C here, so this contour that enters in this object here, are basically the union of these two lines. And what I'm illustrating in these two diagrams is that you can deform this contour to either pick up the poles in this fashion or in this fashion, doesn't matter, you'll get the same answer, okay? So you can deform the contour in either of these two ways. And okay, so you go through the computation, you replace the characters. Then the characters now you can see here, instead of just having sine, then you get sine cubed, and you get a beautiful expression in terms of polylogarithms. If you ever computed a heat kernel in S3 for a massive particle, I'll tell you, you get the same result. Up to this UV, and when you do a heat kernel, you will have a UV divergence, but the finite contributions is exactly this horrendous mess, and that's why I'm writing that horrendous mess, okay? And there you go. On a fixed background, this is computing a one-loop determinant. Very good. Now, we wanted to talk about quantum gravity. So let's move now to what happens if I now turn on G Newton. So that was just on a fixed background. So I need to do various things in order to get there. So it's quite a series of steps. So again, I'm just going to do it on a fixed topology, just on S3. That's the one that we picked. It's the simplest one. But we're going to do also all the perturbative computations around that fixed topology. And there's a few things that you do have to pay really careful attention before you start using Chern-Simons technology. First, as I told you at the beginning, the level is complex. So just be mindful of that. It's not an obstruction, but just don't forget about it. And also, when I use results of Chern-Simons theory, here again, it's important that my background connection is not the trivial connection. Okay, so you have to incorporate this as you try to do this path integral over A left and A right. Okay, and the third point that you might be worried is that usually when people, like the evaluation, for instance, of just a single Wilson loop in Chern-Simons theory usually uses just the normal unitary representations. Here we also have this extra layer that I'm using these funny kind of like non-standard representations. So we also have to make sure that when you insert these non-standard representations in the Chern-Simons path integral, they give you reasonable results. Okay, so there's all these like layers that go through. But okay, we did our homework. And so let's first just talk about the partition function. So this is just a little bit to set up the stage. So we basically did it two ways, just to reassure ourselves that we were getting consistent results, that the results that we were getting did not depend on the method. And so two methods that we used were basically abelianization, which was promoted by Blau and Thompson. And then here we also use supersymmetric localization. Although I don't have fermions, it's fine, but it's kind of a useful way how to think of the path integral. And for the Wilson loop, this was very nicely described in this paper by Kapustin, Willett, and Yakov. So these are the two methods that we use. And just for your comfort, the answers agree with the two methods up to some trivial normalization, okay? So if you don't like the fact that we added supersymmetry, you can focus on this method. Abelianization does not use supersymmetry, and it gives the same thing, okay? Okay, so the Chern-Simons, like, so then the partition function on S3 without the insertion of any matter in this language basically looks like this beautiful expression, where the only thing here that differs from the usual answer is that I'm incorporating, so you go through all the steps, and the data about the holonomies are basically encoded in this H left and this h right. But this basically, this variable sigmas that go in here is basically your metric degree of freedom. Okay, so the integral over sigma is an integral over the reals. That's your integral over g mu nu. Okay, and so you can do this a bit more carefully. You can just do these integrals. This is the answer. So here is the answer for any value of our left and our right. In this computation, it actually, because the holonomies are plus and minus 1, the signs, like this is where you can be a little bit sloppy in this computation, and it didn't matter because the sign doesn't see this. And then this is the answer that you get, and you can check up to one loop that it agrees with a metric computation. Okay, so if you do so this part here is the classical, is the tree level part of the answer. That's what we're incorporating here. There's a background value for the connections, and then you can, if you do the large, the G Newton expansion here, the large K expansion, basically you will see the one loop correction, and then you can also check it with a one loop correction on S3. Okay, and this was done long time ago, so this is not new. Okay, now let's just do a Wilson loop. Okay, before doing the spool, let's just look at a single Wilson loop on these funny representations. So you might worry, because then usually the representations are finite dimensional and SU2. So you might worry what happens if you insert a character of these non-standard representations. And so lucky for us, basically this sign here that you might have worried that it might introduce some pathologies, it actually cancels against one of the signs there. And so then the computation just goes through. And the answer for this is basically this. And here you get usually, so the number that you get here, it's basically the same as you would have gotten in other, for just the unitary representation. So it's like the quantum dimension of the representation. And here, this now is going to be a complex or just a real or complex number, depending on the representation that you're picking. But basically, it's a well-defined operation, okay? And the two methods really, if you go through them, they don't assume anything about unitarity of the representations or not, or them being finite dimensional. So the methods are friendly to the fact that you can insert a different character here and you get a reasonable answer. Okay, so now then we are brave, and you can now say, okay, let's do the Wilson spool. So basically you have the same ingredients. So this first line here is basically this metric part of the connection part of the path integral. And then here I'm inserting this object here that had this integrals over alpha. And here in this answer, so for the two previous things that I did, it really didn't matter that I put that h left and h right were plus or minus 1. It kind of went away. But now it will matter because this alpha, which is a variable that I'm integrating over, is not going to tell me that like whatever signs I had before are going to be shifted because that the signs are going to be invisible because this h was an integer. Okay, so now I have alpha, which is a complex variable that I'm integrating over, times h left. And this is where you will see that if you wanted to reproduce the background like metric and like actually have the field propagating here, it is important that you have that these h's are non-trivial. Okay, now, so what do you do with this? So what we did, so this is an explicit formula. Basically, the way that you have to think about this formula is that I told you how to introduce a field and integrate it out in a sense. Because I basically, the only place where the field now it's like hiding is in this representation. But the things that I have to do are quite explicit. It's an integration over these two variables and the integration over alpha. So basically in this formulation, I have integrated out the matter and just gotten an explicit expression where I just now have to do the gravitational path integral. And so you can do an expansion of it. So you normalize it by the value of the partition function on S3, and then you can read off what the corrections are at any order in G Newton. And so in that sense, you get some long expressions. They're not super illuminating. Thank you. But here I basically just reported, the expressions are a little bit lengthy. As you saw, you get a lot of these polylogarithms floating around. And so I just wrote down, for instance, here, one way that you can interpret this is basically as viewing the corrections in G Newton as a mass renormalization of the field. And I wrote down here basically what is the prediction on how the mass gets renormalized at order G Newton squared. So it's kind of interesting that you don't get a G Newton correction. So you don't get a one loop correction. The first non-trivial correction comes at 2 loops. So that's a precise statement that we can make. Yes.
Prediction value of the log of C scalar, not C scalar.
That's a great question. It's because it's easier to just introduce the characters themselves. So this was computing the log of the determinant. If I wanted to compute just like C scalar, it's the exponentiation of this multi-particle configurations. And then I have to understand basically links. So I have to understand what it means to compute like basically multiple insertions of this Wilson loop, if you want. And that it's in principle, it's doable. There's like, I can say those words. It's like, oh, exponentiate W. It's just that, yeah, you have to regulate them various things when you have these guys, like if you have links and knots. And so that we haven't done. And so the easiest computation for us to do was to just compute the expectation value of this, which is the expectation value of the log, not of the log of like, so yeah, so that's what we're doing. But at least for the leading corrections, it will match. So the first non-trivial correction, it will be the same if you put the log inside or outside. But that's basically, this is one of the things that I know Jackson at least is thinking about, like, oh, how do you do then multiple insertions of this so that you can actually compute C scalar. Okay. And I think I'm very close. Yeah. Oh, this is great. I'm good on time. Okay. So conclusions, basically what did I do today? I don't know. So what I have done is basically, I have told you how to incorporate matter fields in the Chern-Simons formulation of 3D gravity. I did not mention the case of ADS3, but we also, in the references listed there, we also do the case of ADS3. The proposal works as well there. We tested it. Basically, I showed you how to test it in the limit that G Newton goes to 0 to see that it actually reproduces the log of determinants on a fixed background. But we can also compute, in the case of the sitter3, we can actually compute the quantum corrections to it in a very systematic and efficient way. And very kind of miraculously, I don't have a metric counterpart computation to check this against. So nobody has done it to date. But in any case, in Chern-Simons, it was a very simple thing to do. So some future directions, some things that we're thinking about. So I did talk today only about like scalar fields. This basically meant that the Casimirs of the 2 representations of SU2 were equal. Massive higher spin fields will be a nice generalization to make sure that the proposal is robust. There's also an interesting discussion here about a sum over topology. So even in the case of the sitter3, you also have other backgrounds that contribute to the path integral. These are basically quotients of the sphere. Length spaces are regular configurations. And there, the relationship with Chern-Simons theory is more delicate. You do have to take into account some other effects that happen in that case, but then you might also revisit what happens to this proposal and what would happen if you do sums over topologies. If you have those other configurations. You can also think in this context of like cutting open the sphere, especially if then you wanted to do more Lorentzian computations, and think about what happens to edge modes in this context. So usually when you have Wilson loops and you cut it, you basically get, then you get Wilson lines kind of punctured at the boundary, and you get affine representations. And now he's upset. And so now in this context with these non-standard representations, you can also think about like what are the affine representation. Okay, and ADS3 is a little bit more tricky to talk about the quantum corrections, but I don't think, in principle, there should be a path forward to understanding what are the G-Newton corrections in the case of ADS3. Another interesting discussion is the role of higher form symmetries in this language. So Chern-Simons theory has higher form symmetries, has non-invertible symmetries, which are these Wilson lines. So basically, how can you think of this construction, and what do these non-standard representations mean in the context of the role of higher form symmetries in quantum gravity? And then also, as I was asked, that we were really computing this, but we actually want to compute that. So this is also something that you have to keep in mind. Technically, it's a little bit difficult, but I think it's within reach. So with that, thank you.
So thanks a lot. It seemed like this Wilson spool reproducing the one-loop determinant was something that was very specific to free scalar field theory, or perhaps a free higher spin theory in these examples you want to do. Do you have any idea how you would get like the one-loop determinants of interacting theories using this technology?
Interacting theories are in general difficult. I don't have anything too concrete to say. Like I think, yeah, because there might be a way forward, but I don't have anything like really very insightful to say at this moment. It's tough.
So you mentioned this formula relating the one-loop determinant to quasi-normal modes. Can you use this also to extract quantum corrections to the normal frequencies?
Yeah, I did mention that. Sorry, what is the question?
Can you use your final formula to extract the quantum corrections to the quasi-normal frequency?
Yeah, but the thing is that, so the motivation, just to understand why that formula was correct, yes, you use the quasi-normal modes, which is very specific to like that background, but you can actually think about it more broadly. And the thing that is nice, so if you want, you can view it a bit as an inspiration. But the thing that is interesting is that then from the Chern-Simons point of view, I can then like, and it's explicit in how the Wilson spool, okay. At this level, I don't care what A left and A right are. So getting here, it was motivated by this quasi-normal mode method. And basically the quasi-normal mode method is telling you like, oh, you're looking like fields basically transform in a certain way. And then you're looking for like regular configurations in that field space. And that's how you can motivate the quasi-normal mode method. But when you then translated that as a statement in terms of like the connections, I don't have to say that this A left was specifically like S3. Like if you, so in some sense, like the beauty of this is that it's a very simple dependence on the metric. And I don't rely on the specificity of like, you really needed to have like this flat connection or things like that. Like it just becomes like a very like off shell, if you want, statement. And so that's why in that sense, I was able to keep the metric arbitrary and like integrate out like the matter field.
Regarding your last point of computing log of Z, people found similar simplification that reminds me of that for scattering amplitudes in flat space. So I was wondering if you thought about this connection.
For flat space.
Instead of computing the partition function, just the exponential of.
I haven't thought about it in flat space, if that's the question. No. Yeah, we specifically picked SU2 Chern-Simons because I know that I understand what I'm doing at the level of the path integral, or at least I have more resources in order to understand that. If there's some part that is non-compact of the gauge group, then I get nervous. Yeah. Yeah.
So normally in metric formulation, couple to a scalar,
Problem computes some scattering amplitude. I'd have some vertices, and I use usual diagrammatic rules. Here, I mean, can you imagine some diagrammatic description where Wilson spool is coupled to gravitons like this? Like, what picture would you draw to compute some interaction process?
Interaction of what? Of the scalar with the metric?
Yeah. So
Oh, it's what I drew at the very beginning. I'm just thinking that I'm exchanging gravitons.
The scalar represented as a Wilson spool?
Yeah.
Like language we can use to talk about more complicated processes like
There might be, but yeah, I'm being a little bit cautious in that sense because I think I first, to say that with more confidence, I first have to address this last point. So in our kind of like list of priorities, I want to first address this, that I actually have an efficient way how to compute actually the expectation value of set and not of log set. And then introducing these interactions will be something that I can then fantasize in this diagrammatic sense. Yeah, insertions of multiples of these Wilson loops, it's not something unheard of. Like people do these computations, but there's some, yeah, okay. I haven't done it yet, so then yeah. But I could view it in that way, that then basically this like spool is basically, you can view it as like some effective propagator that will capture like something like just, yeah, you will be able to have some Feynman diagrammatic expansion. But I do need to do this first, just to, in my linear mind.
Do you think this unconventional representation is because of the theta or is?
Yeah, it's because of gravity. So actually, you can try to do the same thing with the unitary representations, and you can spool them. It gives you 0. Gravity does not want to couple to unitary representations of SU2. Gravity wants to couple to something that has a continuous mass parameter. So yeah, so that was also kind of nice, that it's not like, oh, I invented this representations because I was like, actually, you don't get the right physics, like, even at the level of the one loop determinant, like, yeah. And the spool kind of, because you don't have like, this cubic order of the pole was kind of important for you to get something non-trivial in the de Sitter case. So that was very fast. Yeah.
Maybe a related remedial question is why are you discussing SU2 Chern-Simons instead of SL2C?
Because I'm doing a Euclidean computation. It's because, well, in a sense, it's because I know what the path integral, I know how to do localization in SU2 Chern-Simons theory. And that's a relevant group for a Euclidean computation. Now, one loop determinants are also, well, not always, but also usually they're computed in Euclidean signature. So it's not so unheard of to do the Euclidean computation. Of course, if you wanted to then, like, I don't know, connect to like cosmological correlators, let's say, and do something more interesting, then I would have to understand, yeah, out of this Euclidean computation, right, how would you cut this and then extend it to Lorentzian signature? That will be a task that is a non-trivial task. But yeah, as a first step, like, yeah, I'm doing the Euclidean setup. And the thing that is powerful is that I don't have to reinvent the wheel, because people already have thought about how to compute the SU2 Chern-Simons path integral quite carefully with all sorts of methods. And then it was for us very easy to then see how to incorporate all these ingredients that make gravity a little bit different from Chern-Simons theory. Well, a little bit or a lot, depending on you.
So can I, so the first half of your talk, can I think about it as like teaching us how to do the world line formalism, but where you write the background metric using the Chern-Simons presentation instead of the metric?
Yeah. Yeah. And I told you what the quantum version of a geodesic distance is.
Since I'm summing over trajectories of particles,
Yeah.
Although you're using the group theory to do a lot of that for you.
Yeah, exactly.
If you wanted to go now, so now then when you make gravity dynamical, I guess if it's okay to maybe first order in G Newton, but at higher orders in G Newton, the matter should back react on the metric. And then is Chern-Simons formulation.
Well, that's basically that you can fully integrate. That's what I meant by integrating out the matter. So I basically made it fully back react on the metric, and then the expressions that I'm writing, it's just exact statement. And this is the, so,
In the Chern-Simons rewriting of the metric, is it, so you say it's, I mean, SU2 is the isometry group of de Sitter, but at higher order, you won't have the de Sitter isometry, right?
that's okay.
So the rule is just I integrate out the matter at one.
Yeah, I was capable of
and then I-
integrating out the matter.
Chern-Simons,
And
the
then
whole
I
order
have
is
to do
in
the path integral.
unit.
Exactly. Yeah.
Okay.
Yeah. So it's, that's basically, yeah. And this is standard in Chern-Simons theory as well. Like if you think of it, like basically when you have these like Wilson loop operator, Wilson line operators, you also think of it at Chern-Simons if you want. Yeah, it's a low energy effective description, but it's a completely healthy, nice QFT. And this Wilson lines are basically integrating out massive degrees of freedom that you might have had like from some other scale. And that's what I'm doing here. Yeah.
I think Alejandra.